Welcome to Chapter 7. The problems that will be due for Chapter 7 are 7-1, 7-3, 7-5, and 7-9. This is a chapter talking about quantum mechanical model of the atom. We'll be talking about the electromagnetic radiation. We'll be talking about certain things that you need to understand about what a wavelength is. So you have a wave, and this is the amplitude of the wave, whereas the wavelength is here from one peak to the next peak is the wavelength, and the wavelength is written like this: frequency, nu. Call it like a new pair of shoes, new frequency. And you also need to know that the frequency is inversely proportional to the wavelength. So this means if you increase nu, the frequency, you're decreasing your wavelength. And that's because both lambda, which is your wavelength, lambda, you'll hear me say lambda, times nu, wavelength times frequency, have to equal the speed of light, which is c, which is 3.00 times 10 to the 8th meters per second. And so in order for this to be a constant, when one increases, the other has to decrease mathematically. The other formulas you need to know for this chapter: E is your energy, equals h nu. H is Planck's constant, and we'll be talking about Planck's constant. It is on your periodic table that you're given. Also, you're going to have a lot of times when you have the wavelength given to you in the problem, but you got to calculate the energy. So what I always do is, just because I already memorized C equals lambda nu, or lambda nu, I just solve in terms of lambda here. So, or nu, I'm sorry. So nu equals C divided by lambda, and I just plug that in. So the other equation is E equals Planck's constant times C over lambda. And that's if you're given a wavelength and you need to calculate the energy associated with that wavelength. If you watch your lecture videos, you understand that different wavelengths have different energies associated. And there's a lot of information that talks about that. Okay, well, let's get started. Your first problem, 7-1. This is section 7.5, page 315. And it's talking about hydrogen atoms. So hydrogen atoms, you can actually calculate the energy of each orbital where the electron's on the orbit using this equation: E sub n, meaning the quantum number of what orbit the electron is on, is negative 2.18 times 10 to the negative 18 joules. That is the Rydberg constant. That is also given to you on your periodic table. That's R sub h. But the equation is basically the constant times 1 over n squared. So that is the equation that you'll need to know. And n can be discrete numbered integrals 1, 2, 3. So basically you have energy, like an energy diagram, and then you have these different energy levels. And the ground state is going to be your lowest energy. Then you can go to a higher energy and another higher energy, and these are basically, a hydrogen has how many protons? 1 proton, and has 0 neutrons. So its nucleus is there. So you can imagine its electrons, n equals 1 would be that orbit, n equals 2. And these energies get higher the further away from your nucleus. And so what happens is How many electrons does a neutral hydrogen atom have? That's right, it has 1. But if you excite it up to like n sub 3, then it relaxes back down. It's going to give you a certain amount of energy. And that certain amount of energy is going to come off into as a wavelength. So that's what you're doing here, is you're calculating the wavelength associated from the n sub 3 to the n sub 2 transition. So when it goes here. And so how do you do this? This is your energy equation related to your n value, your quantum value. And page 319 has combined these equations for E final equals, delta E equals E final minus E initial using this equation. So basically this equation ends up, when you combine it, negative 2.18 times 10 to the negative 18 joules, which is Rydberg's constant, times 1 over the final n value squared minus 1 over the initial n squared. Now, the first thing you want to do is you want to work this part of the equation. So your final here is the wavelength of n sub 3 to n sub 2. So n final is 2. The n initial is 3 because you started at 3. So when you put that in, 1 over 2 squared minus 1 over 3 squared, what does that work out to be? 1/4 minus 1 over 9, and that ends up, if you subtract that, you get 0.13889. And you take that times this negative 2.18 times 10 to the negative 18 joules, you get a delta E value of negative 3.03 times 10 to the negative 19 joules. By the way, this is all worked out on page 319 in your text, I noticed. So you could be following along there. The negative sign, what does the negative sign mean? It means that the atom is emitting energy. So it is emitting energy. That's why you get the lights and the colors, because it's relaxing from n equals 3 to n equals 2. It's emitting energy. And this energy is what you're going to have to calculate. Well, you already calculated the energy, but you're going to put this in to the equation that relates energy with your wavelength. You'll have to do this a lot in this chapter. So once I just remember E equals H nu and C equals lambda nu, and then I solve for nu equals C over lambda, and then I say, okay, E equals, I put this in for lambda, H times C over lambda, and then that's Planck's constant, which I can get from my periodic table, and that is 6.626 times 10 to the negative 34 joules times second. Speed of light, that's also on the periodic table, that you'll be given, 3.00 times 10 to the 8th meters per second, divided by lambda. So we do have our energy. We're going to put this energy in here. But what I've done is something I don't like to do, and that's I like to solve for lambda first. So, because that's what it's asking. So let's just go ahead and isolate our variable. That would be HC divided by E. And so redoing that equation then, 626 times 10 to the negative 34 joules second times speed of light. Now, pay attention here. This E needs to be a positive value because this is just a direction or emittance. So let's put in the positive value here, 3.03 times 10 to the negative 19 joules. Your joules are going to cancel out, your seconds are going to cancel out, and you're going to get your wavelength in meters. So when you multiply these two and divide by that, your lambda is going to be 6.56 times 10 to the negative 7 meters. And we go ahead and calculate that into nanometers because that's what we really like to report our wavelengths in. So what is that for 1 meter? We have 9 zeros for nanometers, and nanometers smaller, so it ends up being 656 nanometers is your answer. Problem 7-2. We're still doing Rydberg equation. Once again, this equation is for the hydrogen atom. So make sure, and then in the ground state, which would be N equals 1. What is the energy of the electron? So you just do E equals negative 2.18 times 10 to the negative 18 joules times 1 over the N squared. And N squared is going to be 1 times 1, right? So that's all going to be 1. So this is your energy. Negative 2.18 times 10 to the negative 18 joules is the energy. Now they're saying consider a hydrogen atom in the excited state of 2sn. 2, which talks about in the end of your chapter, this is n equals 2. It's a quantum number, and it tells you how far the electron is from the nucleus. So there's your proton in the nucleus, and you have an energy shell of n equals 1, and that's the first orbit away from the nucleus, and then you have an n equals 2. And so a 2s1, that's the number of electron, so you have 1 electron. 2 is your n level, so that's the distance away from the proton, your energy shell. And then this S is called, they give you another letter called angular momentum. And this is your shape. And you'll learn that for L equals 0, it's an S shape, and that's just a sphere. Okay, the probability density of finding your electron is in this sphere shape. And that's the way it is for hydrogen. So what is the energy of its electron? Well, for the Rydberg equation, you just do E equals negative 2.18 times 10 to the negative 18 joules times 1 over, and now you do 2 because your n equals 2. So they're saying squared. So you do that first, 1 divided by 4, and then you multiply it by negative 2.18 times 10 to the negative 18, and you get negative 5.45 times 10 to the negative 19 joules. Hydrogen, the negative sign means that you're emitting, emitting, this energy. It's leaving the system and going to the surrounding. This is problem 7-3. The relating energy with wavelength. So what you're going to do is you're going to use the equation E equals h nu, C equals lambda nu, and then of course nu equals C over lambda. You can put that in for nu, and you're going to use E equals h C over lambda. Now, you have these different lights, and these different lights, red light, green light, and blue light, they all have different wavelengths. And since the energy of the light photons vary with the wavelength, we're going to calculate the energy per mole of photons for each of the following colors. This is a very important problem to know how to use because it's also going to relate not only to how to take a wavelength and calculate energy, but you're going to learn that that is the energy per one photon. And the interesting thing about this problem is it says per mole of photons. So you're going to take that number and use it kind of like a conversion factor. So let's start with red light. Red light, when you do this, you have to look at your constants, and C is 3.00 times 10 to the 8th meter per second. So you need to convert nanometers to meters, and then we're going to convert this to the energy of the photon using this equation here. And then we're going to convert that to energy of joules per mole. And then we're going to put this actually in kilojoules per mole. And we're going to do this for each one of them. So I'll work the first one here and then we'll work them on the bottom. So let's do red light. 729 nanometers. And you have 9 zeros nanometers into 1 meters. This ends up being 7.29 times 10 to the negative 7 meters. Now we're going to put that into this equation. E equals, use Planck's constant, 6.626 times 10 to the negative 34 joules times second times the speed of light, 3.00 times 10 to the 8th meters per second. And then we're going to divide this by the wavelength here, 7.29 times 10 to the negative 7 meters. We're going to make sure that our units cancel out, meters and seconds, and we're left with joules, which is correct for energy. And this ends up being, of red light, we'll put red light, 2.73 times 10 to the negative 19 joules. Now go ahead and make this per one photon. Okay, so that's what you found for one photon. Now, the question asks per mole of photon. So then you're going to take this number, 2.73 times 10 to the negative 19 joules per one photon, and you're going to use Avogadro's number, which is 6.022 times 10 to the 23rd photons per 1 mole of photon. And this is going to give you joules. We're going to go ahead and convert it to kilojoules. For 1,000 joule, you have 1 kilojoules. So the energy of the red light, we're going to put red here, energy equals 164 kilojoules per mole. Now, you need to do the same with green light and blue light. So green light, go ahead and convert 525 nanometers to meters. And I showed you how to do that, so we're just going to put this at 5.25 times 10 to the negative 7 meters. And then we're going to put this in our equation. E equals h times speed of light divided by lambda, and that ends up being 6.626 times 10 to the negative 34 joules times second times the speed of light divided by this number here, 5.25 times 10 to the negative 7 meters. You cancel out your units to give you joules, and this ends up being 3.79 times 10 to the negative 19 joules per 1 photon of green light. But we need to get it into kilojoules per mole. So in order to do that, we're going to do 3.79 times 10 to the negative 19 joules over 1. And this is per 1 photon. And we have 6.022 times 10 to the 23rd photons per 1 mole of photon. And then we have 1,000 joules per 1 kilojoules. This ends up working out to be, for green light, 228 kilojoules per mole of green light. So let's put this up here real quick. Okay, so for red light, we said it was 164 kilojoules per mole. For green light, we just calculated it to be 228 kilojoules per mole. And then we do the same for the blue light. And the blue light, the 409 nanometers, ends up being 4.86 times 10 to the negative 19 joules per photon. I won't do that. I'll let you do that. And then when you convert that using Avogadro's number, you get 293 kilojoules per mole. So let's put that up there. And so this is, for the blue light, 293 kilojoules per mole. So which one has more energy? The blue light does, doesn't it? So a 409 nanometer, which makes sense, right? Because it's a smaller wavelength. Smaller wavelength is going to have a higher frequency. Higher frequency has higher energy. 293 kilojoules per mole. See, when you got things in terms of mole, you can compare them. This 293 is larger than 228, which is larger than 164, which makes sense because they have smaller wavelengths. So here it says splitting liquid water into hydrogen and oxygen requires an input of 286 kilojoules per mole. Assuming a mechanism existed in which one photon of light could split one molecule of water, which color of visible light has enough energy to carry out this reaction? So obviously we're looking at for the light energy that's equal to or greater than 286. And the only one is blue light. Blue light. Blue light, because it has 293 kilojoules per mole. This is problem 7-4. Okay, this problem is similar to problem number 44, page 330 in your TRO book. So when you look at this problem, you start reading it, you start writing down some variables you're given. You're given a delta T of 67.7 degrees Celsius. You're given a specific heat of water, CS of water, which is 4.184 joules per gram degrees Celsius. You're getting a density of water, which is 1.00 grams per milliliter. These are some conversion factors. You're given a wavelength of 10.5 centimeters. And you're giving a volume of 0.485 liters. So that's kind of just what you're given. Let's see what it's asking for. So you have a container that has 0.485 liters of water is placed in a microwave. And then it's hit with some electromagnetic energy at a wavelength of 10.5 centimeters. The temperature of the water rose by 67.7 degrees Celsius. Okay, here's the question. Calculate the number of photons that were absorbed by the water. So in order to do that, to calculate your given a wavelength, you know of one equation where it's E equals h nu. C equals lambda nu. Nu equals C over lambda. This goes into that equation. E equals Planck's constant times the speed of light divided by your wavelength. Your wavelength is defined here. Okay, you don't have to worry about Planck's constant because that's a constant given to you. C is the speed of light constant, and you're given a wavelength. But what about E? Okay, so you can solve for your E here. So we're going to do that. But what else are you going to do? You're going to figure out the amount of heat, the energy heat that was needed. Okay, so we're going to figure out how much heat was used. So how we do that, we know equation mass times specific heat times delta T. So you do Q equals your mass. How do you get that mass? You got density of water and you got your volume of water. So in order to get mass, you're going to have to solve density equals mass over volume, and you're going to solve for M. So M equals D times V. M equals 1.00 gram, and this is milliliter, so we need to convert the volume to milliliter, so 0.485 liters. For 1 liter you have 1,000 milliliters, so we're going to multiply this by 485 milliliters. When you do that, your mass becomes 485 grams because the milliliters cancel out and you're left with grams. So now you have mass and you have specific heat and you have your change at T. So you can calculate Q. So let's go ahead and calculate the Q, the amount of heat used for this reaction. 485 grams times the specific heat of water, 4.184 joules per gram per degree Celsius, times your delta T, 67.7 degrees Celsius. The units cancel out here to give you joules, and that becomes 137379.5 joules, which we usually like to use that in kilojoules. Do we do kilojoules? Maybe not. Let's just put that in scientific notation. 1.37 times 10 to the 5th joules. And this is the amount of energy required to heat the water. Now, this is the wavelength here. So now we're going to work on this equation. And then we're going to relate the two. So E equals 6.626 times 10 to the negative 34 joules times second. Speed of light 3.00 times 10 to the 8 meters per second. Divide by the wavelength. Do we want wavelength in meters? No. So, it's in centimeters. 10.5 centimeters. Let's go ahead and for 100 centimeters you have 1 meter. So what does this work out to be? 10.5 divided by 100 is 0.105 meters. So we multiply these two, divide by 0.105 meters. Your energy equals 1.89 times 10 to the negative 24 joules per photon. This is always per photon, okay? And it wants the number of photons. So now you're going to use this as a conversion factor here. You're going to start with the amount you're given, because this is going to be your conversion factor. So you're going to start with the amount of energy required. So you have 1.37 times 10 to the 5th joules over 1, and you have 1.89 times 10 to the negative 24 joules per 1 photon. And so when you work that out, you get 7.25 times 10 to the 28th photons. And that is the number of photons that were absorbed by the water. This is problem 7-5. And this is on page 304. And a key thing here you're going to need to kind of pay attention to is the energy of the pulse divided by the energy of the photon. And that's going to give you the number of photons. So basically you're taking the total energy of the pulse and you're going to divide it by the energy of the photon to get the number of photons in the pulse. Okay, so if you read page 304 and then you try to work this problem, it might be a little simpler. How many photons, once again, how many photons are produced in a laser pulse of 0.107 joules at 613 nanometers? Okay, we have energy and we have wavelength, so we're going to go with our equation, E equals h nu. As always, I do C equals lambda nu. I solve for nu is C over lambda, and then I plug this in. And I say E equals H times C over lambda. And then I say, oh, okay, so I have 0.107 joules is my energy. I have Planck's constant, 6.626 times 10 to the negative 34 joules times second times the speed of light, 3.00 times 10 to the 8th meters per second. And then, actually, I'm sorry, you know what I did? You're not going to use that there. We're going to find the energy of the photon. Okay? That's the energy of the pulse. So just that's energy of the pulse equals 0.107 joules. Okay? And so we're going to divide this by our wavelength. But our wavelength is 613 nanometers. We've got to get that into meters because of our speed of light. So we are going to do 1 with 9 zeros, nanometers into 1 meter. And that ends up being 6.13 times 10 to the negative 7 meters. The meters cancel out, seconds cancel out. And so the energy of a single photon is, at 613 nanometers, is 3.24 times 10 to the negative 19 joules. And then we're going to take the E of the pulse, and we're going to divide it by E of the photon, and this is going to give us the number of the photons. So let's do that. We take 0.107 joules, we divide it by 3.24 times 10 to the negative 19 joules and per photon, and this gives us 3.30 times 10 to the 17 photons. This is problem 7-6. 7-6. Okay. Absorption and emission concepts. Emission. Rank the photons emitted by the following electron transitions from longest to shortest wavelength. Okay, well, I was just looking at this table. A few things. The negative just means how much is emitted, right? So 13.6 is higher energy. The energy of the fourth layer is 0.85, so this is going to be lower energy. Now, when you have a higher energy, this is also the wavelength. A shorter wavelength has higher energy, and a longer wavelength has lower energy. And what you're doing here is you're just going from, and you should know that because energy is proportional to the wavelength. So you just look at the magnitude. Because delta E is a state function, you can go with E of your final minus E of your initial. So here, your energy is given to you in electrovolts, and we're just going to go from 4 to 3. So this is basically negative 0.85 minus negative 1.5, and that gives you 0.65 electrovolts. And that's going to be a longer wavelength because it's less energy. 3 to 2. Okay, so then delta E equals negative 1.5 minus negative 3.4 equals 1.9 electron volts, and that's going to be a higher energy than the previous one. Okay, the next one, from 2 to 1, you go from negative 3.4 minus negative 13.6. And so when this relaxes down, it has an energy of 10.2 eV. Okay, so that 10.2 is a higher energy, and it's going to have a shorter wavelength. 4 to 1, this should probably be your highest, right? So your delta E from 4 is going to be negative 0.85 minus negative 13.6. When you work that math, you see that's 12.75 eV. That is going to be your shortest wavelength. So the emission spectra that comes off when your electron relaxes from a orbital of n of 4 to an orbital of n of 1, it's going to have the most energy associated with it and therefore the shorter wavelength. This problem is 7-7, and the formula that you need for this is Ke, kinetic energy, equals h nu minus your phi. This is, or I'm sorry, phi? Yeah, it's pronounced phi. It's a Latin symbol. This is page 305 that your book talks about it. And what you're given is you're given a frequency, nu, of 4.46 times 10 to the 15th, and that's second negative 1. That's hertz. So we don't really deal with hertz. So anytime you get something in hertz, just make it S negative 1. Your kinetic energy is defined here, 3.40 times 10 to the negative 19 joules. And so you need to calculate phi. And so it's Ke equals h nu minus phi. And so phi is going to be h nu minus Ke. And when you put these numbers in, you get your Planck's constant, 6.626 times 10 to the negative 34 joules times second, times your frequency, 4.46 times 10 to the 15th, second negative 1, minus your kinetic energy here, minus 3.40 times 10 to the negative 19 joules. Now I like to look and check out my units. So S to the negative 1 will cancel out, and your joules minus joules. So you can do that math because they're the same units. So if you multiply this together, you're going to get 2.955 times 10 to the negative 18 joules, and you subtract the 3.40 times 10 to the negative 19 joules, and you should get phi as 2.62 times 10 to the negative 18 joules. Now what is this? This is the amount of binding energy that of your emitted electron or your electrons. Okay, so what you want to do then is asking you what is the maximum number of electrons that could be ejected. So we found the required how much energy is associated with a binded electron. So this is kind of like if you have a whole big piece of pizza and they say, okay, this is the slice, and they give you the area of the slice, and they want to say how many pieces of pizza. So you have to take the whole pizza dynamics divided by your slice of pizza. And then that's going to give you your number of slices. Okay, so what you're going to do now, they give you a total energy here, and you're going to divide by the binding energy of the electrons to figure out the total number of electrons. So what you're going to just do basically is you're going to take 7.08 times 10 to the negative 7 joules, and you're going to divide this by 2.26 times 10 to the negative 18 joules, and that's going to give you 2.70 times 10 to 11 ejected electrons. So once you find that binding energy of the electrons, then you can subtract it from the total energy to find out your ejected number of electrons. Problem 7-8. Okay, I have never worked a problem like this before, so I don't think you're going to see a problem like this. Now, what is good about it is it introduces you to a guy named Heisenberg, and he's on page 313, and this is his equation. This is your position, delta x, times the mass, times your velocity, change of velocity, greater than Planck's constant over 4 pi. And this is Heisenberg uncertainty principle. And he did a good thing. He said we can't be certain. We can't simultaneously measure a particle's position and its velocity at the same time. And this was his equation. You don't have to memorize this equation for the exam. And like I said, I've never actually worked this equation, but basically they're giving you a speed, and they're giving you a position, and they want to know what the uncertainty is. And so basically, and they're giving you the mass of the car, and you don't even have to, these units, you don't even have to worry about these units, okay? So basically, I just worked it like this, 5.0 feet times, because that's your position, times your mass, m, 2,450 pounds, and your velocity, 85.5 miles per hour. What is the uncertainty in the velocity? So basically, if you solve for delta v, instead of put this in here, and you solve for this, you can get delta v is greater than 5.27 times 10 to the negative 35 joules per second. Well, actually, that works out to be 4.30 times 10 to the negative 39 joules per second per feet per pound. And that is not, I guess you can do your conversions and convert feet and pound and try to correlate it with miles per hour. I'm not going to continue working this problem. Like I said, you're not going to get a problem like this on the exam, but do understand that Heisenberg principle is just an uncertainty in position, uncertainty in velocity, and you can't know one or the other. And that's the end of that problem. Problem 7-9. Okay, this is an important problem. And the reason why is because on table 7.5, you need to start memorizing your quantum numbers. And so you have a principal quantum number n, and this is basically your size and energy of your orbits. So you can have n equals 1, 2, 3, 4. Now also on the periodic table, this corresponds to your row numbers. So hydrogen and helium, the electrons are found in the first orbital of n equals 1. Then you go down to your second row, and so lithium, beryllium, they're all in n equals 2. Okay, and so when you see this, like the 1s, this is always your n number, and that tells you that this is your first row on your periodic table. So 4p then would be the fourth row, and it's the fourth energy level away from the nucleus. So here your n is 1, here's 4, here it's 5. Okay, the L is going to be your shape. And L's can be 0, 1, 2, 3, 4. So these can't be fractions. They start at 0 and they work their way up to 4. But this is going to be a shape. And so also other letters associated with S of 0 is an S, L of 1 is P, L of 2 is D. And when you look into your book, you'll see that the S shape is a sphere, and there's one of them. And then you'll see that the P is a dumbbell shape, and there's 3 of them. And so that's what the S is. So the S is your L number, the P is your L number, and the D is your L number. And so it goes from S, P, D, and you have to memorize that. So an L equals 0 is going to be S, and L equals P will be a 1 value, and a L shape that's, and I think of them as a donut, because if you look at the actual shapes, they're kind of funky. And those are also associated, you'll find that those are your transition metals that have those d orbitals. So these are kind of like the houses that the electrons live in, the shape of the houses that you can find those electrons, because this whole chapter is about the electrons. So this would be, D would be an L value of 2. And that is an important problem.